Hello, Mr. Claudia here. Today we are going to begin Chapter 6, our last chapter in the MHF 4U4 Grade 11 Math course, Probability Distribution Functions. And this chapter is really where we combine what we learned in statistics with what we learned in probability to make predictions about different populations. So today we're going to look at random variables. So this is what we're trying to do. Answer questions like this. How many students will pass their exam? How many short circuits will occur on the power line? How heavy is a randomly selected squirrel? We can make predictions based on probability and statistics. We're going to do that by defining random variables. So a random variable represents in number form the possible outcomes which could occur for a random experiment. We always use a capital letter to represent a random variable. There's two different ways we can look at random variables. You've heard these terms before. Discrete, which means it's a countable value. The key word here is count. So our first example of a random variable. Let's let x, remember it has to be a capital X. X is a random variable for the number of siblings a person has. Now, that random variable has a lot of different outcomes. The outcomes are, the first outcome is that you have 0 siblings. The second outcome is you have 1 sibling. The third outcome is you have 2 siblings, etc. You note that the random variable is defined x, but all the different possibilities are lowercase letters. So lowercase letters represent specific outcomes. Now, the number of siblings you have has to be a whole number. It has to be a discrete value. A continuous random variable is something that can take on any value in an interval. I would like to use the keyword measure when I talk about something that's continuous. So for example, let's define a random variable x, which is the time spent on math homework. Your first option, so your first outcome, x, small x1, could be that your random variable x is between 0 and 10 minutes. Your second outcome, that's not very much math homework. Your second outcome could be between 10 and 20 minutes. Your third outcome could be between 20 and 30 minutes, etc., etc. These are all intervals. Let's think a little bit more about random variables. Here I've given a bunch of different random variables. There's the big letter. I want you to think for a second, is this continuous or discrete? So pause the video right now and try thinking about these. Okay, welcome back. So x is the quantity of fat in sausage. This is continuous because you can have any amount of fat. It would be 0.5, 0.55, 0.6, 0.7, 20 grams, whatever. M is the mark out of 50 for a geography test. Well, your mark, assuming you can't get 42.8, right? You can only get a discrete value, usually one number. 50 out of 50, 49 out of 50, 48 out of 50. V is the volume of water in a cup of coffee. That is something you measure. That's continuous. The number of trout in a lake. Well, you can't have half a trout. That's discrete. X is the number of hairs on a cat. That's discrete. And L is the length of hairs on a horse. That's continuous. Now, once you have the idea of random variables, what we can do is, what we're working on in this chapter is a probability distribution. That is, for any random variable, we're going to look at the probability of each outcome. In this course, there's 3 types of probability distributions we're going to look at. Now, when you take a statistics course in university, you're going to learn more probability distributions, but these are the three we cover in the course. The first one is a probability distribution table. This is what we're going to be looking at today. Basically, I have all my outcomes here and the probability that each outcome occurs. So you can see for this table, the third, or x equals 3, that outcome is the most likely. It has a 41.8% chance. The second type of, well, this is actually the third one we're going to look at, the binomial distribution. This is another discrete. These are both discrete. This is a special case, a special table. It happens for certain situations where you have two options, kind of a pass or fail system. We're going to look at this in the second half of this chapter. The other distribution we're going to learn is the normal distribution. This is the one that we're going to learn that helps us with continuous random variables. For example, if I were to measure all of the heights of every student in the class, they would follow this distribution. Most of you would be near the average height, and then you'd have some really short people, some really tall people. So that's coming in a few sections. The reason we have these probability distributions is they help us answer the question, what is the probability that the random variable x is equal to one of these outcomes x? What is the probability that big X is equal to little x? And as you're going to find, it's amazing how we can use math to make predictions. Let's turn the page. Okay, 2 marbles are randomly selected without replacement. Oh, I remember this, right? This sounds familiar already. Great, probability. 2 random marbles are selected without replacement from a bag containing 4 red and 2 blue marbles. Let x denote the number of red marbles selected. Tabulate the probability distribution of x. So, I know questions like this. This is a tree diagram. First, I'm going to draw my the first draw, so I can either get a red or a blue marble. There are 2 marbles. Okay, so 4 red, 2 blue. So the chance of getting a red is 4 out of 6. The chance of getting a blue is 2 out of 6. That's the result of my first draw. Now we're going to draw again. I can get either red or blue, red or blue. But this time my probabilities change because of the without replacement. If I take out a red, there's 1 less red, so now I have only 3 out of 5 probability of getting red. Here I have 2 out of 5. This becomes 4 out of 5 and 1 out of 5. We've done this before. So you see the 4 outcomes. Red, 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 blue, blue, red, blue, blue. Let me find the probability of each of those branches. So the probability of red, red, well that's, I multiply, so 4 over 6 times 3 over 5, which gives me 12 over 30. The probability of red, blue, which is 4 out of 6 times 2 out of 5, which is 8 out of 30. The probability of blue-red, which is 2 over 6 times 4 over 5, which is also 8 over 30. And finally, the probability of blue-blue, which is 2 out of 6 times 1 out of 5, which is 2 out of 30. Sorry, I should write second here. These are all my probabilities. It should be no surprise that all of these probabilities add up to 1. Because this is all my different options. So this is the probability question. You guys should know how to do this. But now we're talking about a probability distribution for big X. So let's just remember, X is a random variable, which is, in this case, the number of red marbles selected. So what are the different possibilities? Well, you could have an outcome where x is equal to 0 red marbles. You could have a probability of x having 1 red marble, or you could have 2 red marbles. So what's the probability of getting 0 red marbles? Well, oh, that's right here. That's the blue boo option. The probability is 2 out of 30. What's the probability of getting 1 red marble? Well, it would be the red-blue branch or the blue-red branch. So it'd be 8 out of 30 plus the other branch, 8 out of 30, gives me 16 out of 30. Finally, what's the probability of getting 2 reds? Well, there it is. It's 12 out of 30. As I told you, we tend to represent probabilities, discrete probabilities, as a table. So I'm going to take what we just did and represent it in a table like this. Well, I'm going to do a horizontal table just because of the space, but I'm going to represent this distribution as a table. I need a ruler, draw a nice table. Okay, so I have all my different outcomes, 0, 1, and 2, right? That's the number of red marbles. And the probability that the random variable is equal to those outcomes, it was 2 out of 30, 16 out of 30, and 12 out of 30. And it's no surprise to us, this is an important matter, the probabilities add up to 1. And that's a nice thing about the probability distribution table. It allows us to quickly know the probability that something's going to happen, or of a random variable being a certain outcome. Great, and that's how we present it. And there's our one formula that's important for today. It's saying for any random variable where all the probabilities are between 0 and 1, if you add, remember this means sum, the sum of all the probabilities is equal to 1. The sum of the probabilities of all outcomes is 1. This should not be a surprise. And this formula, I believe, is on your formula sheet. Let me just double check. So oh, nope. It's not on your formula sheet. So you're just going to have to remember it. But I mean, you should know at this point, right? We've been doing probability for quite some time. All the probabilities should add up to 1. Let's do one more question. What I like about this chapter is we get to actually use math to make predictions about the real world. A country exports crayfish to overseas markets. Crayfish is like a fish. The buyers are prepared to pay high prices when the crayfish arrive still alive. If X, think of like lobster, crayfish, like lobster. We want to eat them, we want to buy them alive. So the company that exports these crayfish, they know the probability, okay, X is the number of deaths per dozen crayfish. So they know that X is number of deaths per dozen crayfish. So for every 12 crayfish, the chance that 0 of them are going to be dead, so they're all still going to be alive, they know it's 54% chance. They know they have a 26% chance that one of the crayfish in the box of 12 is dead. They know that there's a 15% chance that 2 of them are dead. They know 0.01 that 4 of them are dead. Very small, 0.01 that 5 of the 12 are dead. They want to know what's the chance that 3 are dead. Well, we can figure this out, right? We know that the probabilities, if I sum them all up, it should equal 1. So that means that 0.54 plus 0.26 plus 0.15 plus k plus 0.01 plus 0.01 plus 0 is equal to 1. If I add up all of those numbers, so 0.54 plus 0.26 plus 0.15 plus 0.02 gives me 0.97 plus k is equal to 1. So I get k is equal to 0.03. In other words, the probability that x is equal to 3 is 0.3. So interpret the meaning. What does this mean? This means the probability of 3 deaths per dozen is 3%. Imagine this data would be useful to the company or the country exporting crayfish. They would know then, what to expect, how many, people to hire to call these countries and make sure they're happy and that they get an extra crayfish, or they would know how often their orders are going to be rejected because they know these statistics. So your homework for this section, this is our first lesson in this section, so we haven't done too much, but you are going to have to use this property that we did. This we learned this addition of all the summation of all the probabilities. So you're going to do page 522, number 1 to 10. Do not do number 2C. I forget why. I think it's a pain. It's way too much work. Good luck with that, and we'll see you next time.